Hello everyone, I am Rahul Chandlia, and in this next lecture of Internet of Things we will discuss the software defined network. So what is software defined network? It is basically, to understand the software defined network we have to understand what is a traditional way of uh, traditional architecture of networking infrastructure, and how software defined network brings changes in this technology. In this in traditionally, we in this figure we can see the traditional network infrastructure. Uh, from source to destination, we have multiple devices like the edge router, switch, managed switch, network load balancer, deep packet inspection. So our data flow through these switches and component devices and reach to the destination. Every switch or every devices perform its some functionality. So how to define a network path, we have to basically define two things. First is every switch has to decide from what, if the packet is coming from particular input port, uh, to which neighboring switch it has to transfer it, and then this decision is led by some logic, some algorithm, decided by some algorithm, uh, which has to consider the total infrastructure of the networking, total traffic of the networking. So we can divide this whole things into that. But this component logic, this logical decision is implemented basically in a distributed way. Means every routers or switches shares their information, and in every routers these algorithms are implemented. The network SDN basically separate these both uh, step. Uh, so in traditional internet networking, the data plane and the control plane. The data plane that I have said, what is basically the input-output table of the data, and control planes are control planes. Planes means the algorithm that decide what should be this table look like, are unified. So in traditional network, both this data plane and control plane are unified. When the system needs to add or remove another nodes or set up a new data path, many of the dedicated systems need to be updated with new VLAN setting, that is VLAN, virtual LAN setting, and QoS parameters. QoS parameters and EOS is the quality of service parameters, and we have also EOS parameter, which is experience of service parameter. These two basically define what is say the decision policy of the networking, what should be. So parameter access control list, root, firewall, pass through. These are the various definitions. Limitation of conventional network architecture. Complex network devices. First is the complex network devices. The devices, router or switches become very complex because it has not only to decide the input or output table of the data uh, flood, but also implement the algorithm uh, in a distributed sense. So complex network devices. Conventional networks are getting increasingly complex with more and more protocol being implemented to improve link speed and reliability. Interoperability is limited due to the lack of standard and open interfaces. The conventional networks were well suited for static traffic patterns and had a large number of protocols designed for a specific application. For IoT applications which are deployed in cloud computing environment, the traffic patterns are more dynamic. Next is the management overhead. The network manager find it increasingly difficult to manage multiple network devices and interfaces from multiple vendors. Upgradation of network requires configuration changes in multiple devices. That is, devices are purchased from different vendors, and their upgradation or management is difficult. limited scalability. The virtualization technology used in the cloud computing environment has increased the number of virtual hosts requiring network access. The analytics components of IoT applications run distributed algorithms on a large number of virtual machines that required huge amount of data exchange between virtual machines. Such computing environment required highly scalable and easy to manage network architecture with minimal manual configuration, which is becoming increasingly difficult with the conventional network. So to sort out these difficulties, here comes the software-defined network. Basically, software-defined network is an emerging paradigm that promises to make complex IP network more manageable and flexible by breaking vertical integration. Vertical integration is where our control logic and the data plane are tightly coupled, are bundled together, separating the network's control logic from underlying routers and switches, promoting logical centralization of network control and introducing the ability to program the network. The separation of concern introduced between the definition of the network policy, their implementation in switching hardware and forwarding traffic is key to the desired flexibility. By breaking the network control problem into tractable pieces, SDN makes it easier to create and introduce new abstractions in networking, simplifying network management and facilitating network evolution. So what are the main characteristics of the SDN software-defined network? The first one is the control plane is decoupled from the data plane. That is the most defined characteristics of the SDN. That is control plane. The algorithm part, the decision-making part is basically different from the data plane. Data plane hardware becomes simple packet forwarding devices. So now previously the complex router becomes simply the packet forwarding devices in SDN network. All forwarding decisions are flow based rather than destination based. So the forwarding decisions are taken using the flow based. A flow is a set of packets that match a criteria or filter. All packets in a flow are treated with the same forwarding and service policies. Flow programming allows for easy scaling and flexibility with virtual switches, firewalls, and middleware. The control logic is also known as the SDN controller. This software version of legacy hardware is capable of running on commodity hardware and cloud-based instances. So this algorithm basically runs on the say cloud or commodity hardware. Its purpose is to command and govern the simplified switching nodes. The control logic is also known as SDN controller. The software version it is basically repeated. Network application software can reside over the SDN controller through a northbound interfaces. What is northbound interfaces? Basically, we'll describe later. Basically, whatever the application software, that is the service we need to provide using this infrastructure are basically are connected, are attached with the SDN controller, lie above the SDN controller logic. This software can interact. These services are like deep packet inspections, firewalls, and load balancers. So in this picture, basically the architecture are basically defined. So here see the lower part are basically in traditional network. This lower part basically play the role of both control logic and the data flow logic. In SDN, control plane are separated from these physical devices. So these physical devices just act as the data forwarding devices, and this constitutes the data plane part of the SDN. Then the logical part is which is deployed in the cloud instance in the control plane part. So we have again the interfaces are between the control plane and data plane is the southbound API. This is known as the southbound API, and interfaces above the control plane and the functionality various application service is known as the northbound API. So northbound API is the interface through which we interact with the control plane, and southbound API is the interfaces through which control plane interact with the data plane. Key elements. So what are the key elements of SDN control network? Centralized network controller with decoupled control and SDN planes. It is centralized network controller with decoupled control and data planes and centralized network controller. The network administration can rapidly configure the network. SDN applications can be deployed through programmable open APIs. This speed of innovation as the network administrator no longer need to wait for device vendors to embed new features in this proprietary hardware. So centralized network controller is basically important. Again, these centralized control network decisions are not basically located on single physical devices. It can be implemented in a number of in a cloud or number of say physical computer. Programmable open APIs. SDN architecture supports programmable open API for interface between SDN application and control layers. Northbound interface. The northbound interfaces, remember, is the interfaces through which we interact with the control logic part. So with these open API, various network services can be implemented, such as routing, quality of service, access control, etc. Standard communication interface. This interface is basically between the control southbound interface, also known as southbound interface. Through this, the control logic interact with the data plane. SDN architecture uses standard communication interface between the control and infrastructure layer, that is the southbound interface. OpenFlow is a popular example of this API, which is defined by the Open Networking Foundation, is broadly accepted SDN protocol for the southbound interfaces. With OpenFlow, the forwarding plane of the network devices can be directly accessed and manipulated. So the device manufacturer, the device vendor basically implement the OpenFlow or other similar interfaces on the devices, and the control logic basically interact with these interfaces to control the flood of the data. So what are the benefits of the SDN? The first one is the service chaining. This allow a customer or provider to sell a service a la carte, that is means on demand. Whatever you have demanded, you have to pay for that only. So cloud network service such as firewall, deep packet inspections, VPN, authentication service, and policy broker can be linked and used on a subscription basis. Some customers may want a full set of features. Others may not choose any or may change their configuration routinely. Service chaining allows for significant flexibility in deployments. Another is the dynamic load management. SDN enjoys the flexibility of cloud architecture, and by design, it can scale resources dynamically depending on load. This type of flexibility is crucial for the IoT as architect. Need to plan for capacity and scale as number of things grows exponentially. Only virtual networking in the cloud provides the ability to scale capacity when needed. So whatever we have, the advantage of the cloud computing, we basically imitating the cloud architecture into the networking infrastructure. So we, in order to enjoy that flexibility and the scalability. So number of equipments are easier to add. Now upgradation become simple. So these factors and also the dynamic traffic can be handled in a better way. So bandwidth calendaring. This allows an operator to partition data bandwidth and usage to specified times and days. This is pertinent to a IoT as many edge sensors only report data periodically or at certain time of day. Sophisticated bandwidth sharing algorithm can be constructed 2 times less capacity. So this is basically very important for IoT because the bandwidth, the traffic can depend on the time, and it can be periodical. So in we can allot the bandwidth, uh, the future bandwidth in present, basically. So next topic is SDN architecture, which we will continue in the next lecture.